Now we will look at an example from physics. Imagine a bathtub. And there is some water in it, which does happen sometimes. Namely, there is V0 liters, so that's the volume, at time 0. Also, at time 0, we do something, we pull the plug. And as you can expect, the water starts pouring out and the volume will be changing, namely decreasing. But I do not know yet officially. So we will see what's the volume doing, depending on time. That's our question. Well, to answer this question, we have to investigate what's happening within short time intervals. So we'll look at specific times and ask a good question. What's happening there? And we see that if we fix some time interval of length, let's say delta t, a short time interval, then within this time interval, the water will pour out and form a shape. It will form a tube, or perhaps a tiny cylinder if you want. And the volume of this water in this cylinder or in this tube actually tells us by how much the overall volume decreased. So the change in volume, delta V, will be negative because it's decrease. Okay, what's the volume of this shape? Well, we know the area of the base, because that's the area of the hole. We can measure it. Let's call it little a. And this, the base, has to be multiplied by the length of the tube. Now, what is the length of the tube? Well, let's imagine how it goes. At a specific time, we start our stopwatch, and there are some molecules here at the hole. And they start flowing, and when we stop the stopwatch, the time delta t is over, they are just here at the end. So the length of the tube is exactly the displacement or the distance which was covered by the molecule of the water. Now it has a certain specific velocity as it goes through the hole, let's call it v, and then it runs with this velocity for time delta t. And that's our formula. Very nice. Now we divide by delta t. Which gets us to the position when we start arguing that delta t should be actually very small. Because if it's a little bit longer, then this tube is longer, and as the molecule goes down, gravity is acting on it and increasing the velocity v. So it would not be constant anymore, it would change, and that would make our formula much more complicated. We do not want that. So we are considering just very, very tiny time intervals. In fact, the best time interval is the one which is the shortest possible, which is dt. So from delta, we will pass to d, differential, infinitesimal, and dv over dt, that's actually the derivative. Very nice. That's the beginning of a differential equation. Unfortunately, there is dv at the end, which we don't like. That's a new variable, we don't want to see that. Okay. So we go to physicists and we ask them, okay, what's the water? What's the velocity of the water flowing out of the bathtub? And they tell us, well, there is something which is called Toricelliho law, and Toricelliho law says that the velocity is proportional, directly proportional. So there's some constant to square root of the pressure. And this constant, it incorporates many things like the shape of the hole, the viscosity of the water, things like that. Because it need not be a water. Let's say you have a bathtub of jelly, or, well, that wouldn't work too well. Water. Let's make it water. When I was at elementary school, they taught me that the pressure, which is here, is caused by the water column which is above it. So this height is very important. And the formula actually reads, here's the C, the pressure, the hydrostatic pressure, is the density times gravity times h, which is the distance between the hole and the water level. So far so good. Constant, constant, constant. We can pull them all together, lump them into one constant c tilde, and then the square root of h. So we moved from velocity to something else, but we are still not happy because h is not in our differential equation. But when we talk about h, we are really close to volume because they are related. You can calculate the volume and as it depends on the height, on the water level. Or vice versa, that would be nice. Unfortunately, it's not easy for a bathtub because it's sort of roundish. the shape is very complicated. Here is an assumption. We will assume that our bathtub actually has vertical sides. And then there is some bottom, which has known area A. We can measure it again. Now, that's not the typical bathtub, so let's speak about something else instead. It could be a barrel. Barrel is round, it has flat sides, it has a bottom, yeah? Or it could be fishbowl, rectangular box, fishbowl. Yeah, you can buy fishbowls like that. Anyway, here is the water level, here is the depth, and there is a very nice formula then. Volume is the area times the depth. Very simple. And from here, depth is 1 over A times the volume. And we can substitute it into this formula. 1 over A appears here, and I connect it with my constant. So yet another constant, C hat, square root, volume. And that's how we like it. That's a nice formula for velocity because we can merge it with this equation. And we get that V prime is minus, okay, there will be A, and there will be C hat, so that's a new constant, let's call it K. Minus K square root of V. Very nice autonomous equation. Definitely separable. And just out of curiosity, K is positive. This may come handy. Can we solve it? Definitely. Let's have a look at it. dv over dt is negative k square root of v. Well, we want to divide by the square root, and we know, because we've been trained to think about it, that we should worry about the division by 0, and we get a stationary solution. Okay, so that's out of the way. And we can move to the second case, when v is not 0. Okay, dt to the right, square root to the left. dv over square root of v is minus k dt. We attach the integrals. And we integrate happily. 2 square roots of v is minus kt plus c. Then I divide by 2. Square root of v is minus 1/2 kt plus 1/2 c. I don't like that. Okay, so this will be c tilde, and this will be c. Okay, c is 1/2 of c tilde. It looks much better. And finally, v, as it depends on time, is c minus 1/2 kt, that all squared. That looks good. Let's think about it. That's a parabola. It's a nicely shaped parabola because it's just some bracket squared. So it's negative, but it touches the x-axis. It can be 0. Where? Well, let's have a look at it. When is this 0? It's 2c divided by k. And here is our parabola. That's assumed to be a solution. But that's strange, isn't it? Let's see. I have some volume, V0. I pull the plug. The water starts flowing out, so I have less and less water in my bathtub. Then it's empty, and then it starts filling up again. This is weird. And one should ask, okay, what's wrong here? That's a very natural question at this moment. Well, there are two possibilities. One possibility is that all the work was mathematically correct, but the model wasn't really all that good. This can happen sometimes. And then we just take away from the model things which are applicable and we ignore the rest. However, here we actually made a mistake in mathematics. But it is a mistake which is in a way hidden from us because we never saw it before. When we do equations at school, they are usually nice. And also when we do equations in applications, they're usually also nice. There are two things happening here which are not typical, which are special. And if you are not aware of them, if you are not ready for them, it's easy to overlook them. When we are in doubt whether something is a solution, we can always check. So let's check. I take this formula, I substitute it on the left. I'm supposed to take the derivative. So it's twice c minus 1/2 kt times, and now we have to multiply by the derivative of the inside function. So it will be minus 1/2 k. And what we get, okay, 2 cancels, it will be minus k, c minus 1/2 kt. That's the left-hand side. Now let's have a look at the right-hand side. We see minus k. That looks promising, definitely. And then there is a square root of v. We should take square root of something squared. Square root and square, do they cancel? The answer is unfortunately not. They create an absolute value. And when we compare, we can see that these two are not the same in general. So this formula actually does provide us with a solution as long as these two expressions agree, which means this expression should be non-negative. And then we do have a solution. This is really tricky. This is mean, even. Treacherous. Can I somehow see it? Perhaps I overlooked something. Well, how do we determine the region of validity? Usually we do it like that. We look at the equation and we ask, is there any restriction? And of course I can see one. V should be greater than or equal to 0. That's a definite restriction. Yeah, that's true. For any t, I could put t belonging to R and it will still work. Okay, so far so good. What do we do next? Well, we look at the answer and we ask, is there something wrong? And the answer is no. So that's what we normally do. But in fact, we should also scan the procedure for restrictions. And as we are scanning it, we can notice that square root of v, that's a non-negative number. This expression should not be allowed to be negative. Minus 1/2 kt plus c must be greater than or equal to 0. And that's another condition that we overlooked. But it's hidden there. This is really devious. Okay, I move it to the right. T should be less than or equal to c over k. We saw that before. That's the vertex. So those two conditions, they're actually telling us that our solution is only good here, up to this point. It's not good here on the right, unfortunately. Well, that's life. I talked about two problems here. That's just the first one. We overlooked one condition. There is a second problem. I talked about it in previous lecture on analyzing solutions, the section about Picard's theorem. We have two branches here. When v is 0, we get a stationary solution. When v is not 0, we get another solution. But it may also happen that there is a solution which is sometimes not 0 and sometimes it is 0. Well, actually, that's the one. This solution is sometimes, namely over here, equal to 0. So the two families of solutions, they actually meet. Again, that's something that we normally do not see, but here it happened. And we have to know what's going to happen next. What's the reaction to such a situation? Well, we should inquire about the nature of this meeting. There are essentially two different situations. One situation is that you have one solution and another solution, and they meet like that. And if this happens, then you don't have to worry, because each solution simply goes its own way. So that's a nice case. If something like that happens, you don't have to worry, no extra work needed. However, it's also possible for one solution to go like that, and another solution to go like that. Or perhaps you have one solution like that, and another like that. And when this happens, then you're actually allowed to jump from one solution to another. Okay, they should merge here. They should go through the same point. So you could start here, and you can here choose which way, in which way you can continue. And the same here. You start, and here you can choose the branch. And this is what's called gluing solutions. You have segments of solutions, and you can glue them together in any way you want. How do you recognize these two cases? Well, you inquire about the slope of the two solutions at the meeting point. If the slope is different, you don't have to worry. If the slope is the same, you do have to worry. Okay, we have our parabola here. And we have the stationary solution. They meet here. What are the slopes there? Well, the stationary solution has slope 0, that's obvious. And the parabola, if you differentiate and so on, it also has a slope 0. So that's the meeting place of two different solutions. And therefore, we can glue them together. This solution comes here and stops, but we can glue it with the stationary solution, and it actually goes on like that. And it's mathematically correct, and it also makes sense from the physics point of view, or the bathtub point of view. So that's very nice. So how would I write my solutions? Vt is, well, first of all, I can follow, if I want, the parabolic part. Well, actually, since I'm writing it now, may I introduce V0? That's a good question. Yes, let's introduce initial condition. So let's introduce it here. If I know that at time 0, the volume should be V0, how does it work? Well, the volume should be when time is 0. This should be V0. C is square root of V0. That was easy. So that's one possible formula that we can follow, but we can only follow it down to this vertex. So T belongs to interval 0, and it's 2c, yes, 2c. 2 square roots of V0 divided by k. And then we switch to the other solution. And then there is the second possibility that we simply take the stationary solution. But it is actually included, because by changing C, we can change the position of the vertex, and if we put it here, we are simply following the stationary solution. If we put 0 for the initial volume, then this number will be 0, this number will be 0. So this part will be non-existent, going from 0 to 0, and then you go from 0 using the stationary solution. So we were lucky, and the stationary solution as itself actually got included in this formula. However, that's only because we decided to start our exploration at time 0. Notice that if we were just mathematicians, if we didn't know anything about applications, somebody just gave us this equation, then we would actually have to include two types of solutions. This would be one where we would have parabolas going all the way to infinity with any position, and then we would continue using the stationary solution. So that would be one family, and the second family would be the stationary solution. Now this cannot be obtained by starting with parabola because we go all the way to negative infinity with time as a mathematical solution. Okay, so that was interesting. There were some really devious things happening with such a simple differential equation. By the way, this model is quite good for water, definitely, and you can try it at home. You need a rectangular fishbowl. Fishbowl is a good thing. Rectangular fishbowl, it has to be transparent. You've got some water here. You drill a small hole here, but you plug it momentarily, and you draw lines here which should be regularly spaced. Let's say 1 centimeter apart or something like that. And then you take your watch, and when the time is, let's say, 0 somewhere, you pull away the plug and you put a dot here. You wait 1 minute, the water level will go down, and you mark the new water level by a dot here. You wait another minute, water goes down, and you mark the water level here. And you keep doing like that. You keep marking the water level, going from line to line. And what you should get is essentially the shape of a parabola. Actually, the shape here will not be quite precise, because when there's just a little bit of water in your fishbowl, then there will be some other phenomena from physics entering the play. So the Toricelliho law does not follow quite precisely anymore. Things will get complicated. But if you ignore this part, and if you look at the part where there was quite a bit of water, then you should really get a nice parabolic shape. So that's the bathtub problem, or the Toricelliho problem if you want. A very nice differential equation with some surprises. Okay, let's go for our last example. We started this chapter on differential equations with an example of a free fall as an inspiration. And it was a very simple example. But we have learned some things since then, and let's have a look at a more sophisticated version. We start by introducing y-axis, which actually points upwards. That's how we measure elevation. There's an object here. We release it or we flip it in some way, and it starts behaving according to the gravity law. And we had a formula for that. That's how we started this chapter. But this time, the elevation is measured in the opposite direction, so we have to put the minus sign here. The elevation goes up, and therefore the acceleration also goes up, but the gravity pulls down. Makes sense. To make it even better, we are going to ask, what are the major influences? And the major influences are the gravity, but also the air resistance. As long as the object is slow, then perhaps this formula would work quite well. But once it picks up speed, we have to really worry about the air resistance. We have to ask physicists, and they tell us, well, the air resistance is proportional, directly proportional, to the square of velocity. This proportional constant, it hides many things. The density of the air, the shape of the object, the cross-section of the object, these are the major factors. What is the sign here? That's a good question. The air resistance, or the drag, always goes against the movement. So the sign here can actually be plus or minus, depending on what the object is doing. If we flip it up, it keeps going up for a while, and then it goes down. So right here, at the highest point, our differential equation would have to flip the sign, which is very unpleasant. How do we do it mathematically? It's not possible. We would have to solve it as two separate problems, which can be done, but it's complicated. So I'm going to make an assumption. I'm going to make the assumption that the derivative is negative. What does it mean? Well, it means that it goes down. So we are just releasing, or perhaps flipping down, some objects. These are the trajectories that we are interested in. And then we can simply put plus here, because if those objects are falling down, then the air resistance pushes them up. That's the basic differential equation, and it's a second-order differential equation, so separation doesn't work for it. We will learn how to solve some higher-order differential equations later on, but this one is not of the right type. So in this course, we will not learn how to handle it, so that's a good one. It's one of those really good ones. And people who worry about free fall with air resistance, like people in NASA who have to put things up or catch them when they go down, they have to solve things like that numerically using computers. And we will have a little lecture on how to solve equations of higher order numerically. So we will see examples like that later on as well. For now, why am I showing this example now when we don't really know much yet? Well, here is a little trick. Notice that there is no y in this equation. So I can use substitution. I take y prime and I hide it as v. What is v? Well, that's the velocity, actually. Now, the calculations in this example are not going to be exactly friendly, and I will be using tricks to make them a little bit more palatable. And here comes the first one. When I talk about velocity of an object which falls down, I'm naturally thinking of the downward direction. So that's what I'm going to do. I'm going to put minus sign here to reverse the direction for the velocity. And now, let's substitute. Y double prime is actually minus v prime. And on the right we have minus g plus k v squared. And that's a first order differential equation. Let's play with it a little bit. V prime is equal to g minus kv squared. And one more change. I'm going to integrate soon. How do I know? Well, there is no t or no x on the right. This is an autonomous equation, which is automatically separable. I can take this whole factor and divide, and all the v's will be on the left. So in order to make my life easier, I'm going to remove the factor in front of the variable, because for integration, this causes sometimes complications. So here is the form that I really want to see. When I factor out k, there will be g over k here, minus v squared. And now I look at it and I say, okay, that looks like a nice separable equation. Let's play. Okay, first I noticed that I can make the right-hand side 0 by a smart choice of v. So there are some stationary solutions. Vt is equal to plus or minus square root of g over k. T greater than or equal to 0. Very nice. Okay, let's move on. If v is not plus or minus square root of g over k, then we can do the separation and we get dv over. Okay, I'm going to keep k on the right. So on the left there will be just g over k minus v squared integral, and on the right there will be this k dt, and that's about it. Okay, I would like to factor out, I know the roots here, because I have to use partial fractions decomposition. That's a polynomial of degree 2. Okay, that's life. How will I play it? How will I play it? Okay, I will do several tricks. One trick is that I multiply both the left and the right hand side by minus so that v has a positive sign in front of it. I like it that way. And the second trick I'm going to do, I will introduce a for the square root of g over k. That's a fairly convenient notation, obviously, here. So, how will it go? There will be dv, there will be v square minus a square on the left, definitely. And then there will be integral minus k dt. That looks fairly nice. Okay, now the partial fractions decomposition. V minus a, v plus a in the denominator minus integral k dt. Now I left some room here because I will do another trick. I have been doing this partial fractions decomposition a lot in my calculus course, and students as well, and we have some experience with how this will go. So I know from experience that it would be really nice to have 2a here. And if I want to have it here, I also have to have it over here. Okay? Let's play. Now I do the partial fractions. V minus a, v plus a, dv should be, and let's play here, this is minus 2, and a is actually the square root of g over k, so k's can be put together. This is square root of gk times t plus c. So far so good. Okay, on the left. Here, the number on the top is obtained by covering up this, and here I substitute the root of this, which is a. So I'm substituting a, 2a, it's 1. See, that's how nice it is. Okay, let's play here. I cover up, the root is minus a. Minus, 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 it's negative 1. Here we go. Let's move on. This looks like a calculus review. Logarithm of v minus a minus logarithm of v plus a is equal to minus 2 square root gk times t plus c. Does it look familiar? The right hand side looks good. Okay, let's move here. Okay. Logarithm of v minus a divided by v plus a should be minus 2 square roots and so on. So far so good. Now I apply exponential to each side and I do the plus minus trick. Plus minus trick, exponential and exponential. Okay. Now we will introduce constant d, which right at this moment should not be 0. And we have to isolate v from here. So I'm going to multiply out. Perhaps I can introduce another symbol here so they don't have to copy it all the time. Okay, v is on the left. There is one v from here, and after I multiply, I will move this to the left. A is on the right. A from here, A from here. These two look remarkably similar, and that's as it should be. So I think it's hopeful. And I think we are ready to write the answer. So I'm going to replace A with its original meaning. Square root g over k times fraction 1 plus d e2 negative 2 square root gkt divided by 1 minus d e2 negative 2 square root gk times t, where t is greater than or equal to 0. Okay, let's see. What happens if I put 0 for d? That's a good question. If I put 0 for d, then this disappears. 1 here, square root of g over k. I'm getting one of these stationary solutions, which is nice, not the other one. Yeah, that's interesting. But anyway, I don't really care about the other one. Why? Well, because, here we go, one stationary solution, another stationary solution. So these are actually equilibria. But we are only interested in the cases when the stone falls down. We are never interested in negative velocities. So this is really not relevant. So I'm really interested only in this upper part. Let's have a look at the formula here. Let's say differential equation which is autonomous. Let's talk about slope field. When v is really large, close to infinity, then this will be negative infinity, negative derivative. So it means decreasing velocity. Here, positive. I can imagine that velocity is about 0. And when velocity is about 0, then the derivative, I can see it here perhaps better, then the derivative is positive. Okay. One could play also with things down here, but we are not interested in them anyway because they are not relevant. This looks like a stable stationary solution or stable equilibrium. Is it borne out by our solution? Well, let's have a look at it. What's the limit of the velocity as t goes to infinity? Well, if t goes to infinity, that's a positive constant, times infinity is plus infinity, but there is minus in front of it. Exponential to negative infinity goes to 0. 0 here, and we get this. This is so-called terminal velocity. By the way, we have an analytic solution for this differential equation, which means we have an analytic formula for the velocity. If we have a formula for velocity, we can recover the position by integrating. Well, just look at it. Good luck integrating. Try it. It's not pleasant. Okay, here we go. Terminal velocity is very important. That's the moment when you have a velocity so that the force of gravity and the force of drag of air resistance are exactly negated. So once you reach this, you stay like that. If I remember correctly from what I read, it takes about 1 or 2 minutes for a human being to reach this terminal velocity, and it's about 200 kilometers per hour, which is rather a lot. It depends on your shape and other things. There have been people who actually had to experience this because, let's say, they were skydiving and their parachutes didn't deploy, things like that, or during the war when the airplane was shot up and they just fell off the airplane without parachute. There are cases like that. So it's really good to know your differential equations because the good news is it takes several minutes to actually reach the ground if you start, let's say, at 2,000–3,000 meters. So you have lots of time and you have a time to write down the differential equation, you solve it, you find a formula for the terminal velocity and you start thinking, okay, I'm up there, the Earth is getting nearer and nearer. I want the terminal velocity to be as small as possible. What can I do about it? Well, gravity. Can I make the gravity smaller? Probably not. Okay, another try. Can I make K larger? I want K large. Well, that's the air resistance built into it. So the cross-section and the shape. So what you want to do, you want to spread as much as possible. You spread your shirt, you spread your jacket, you spread your ears. If you have hair, it's a good idea to let it out. You make a shape which is not very aerodynamic, and then you need a lot of luck. And some people had lots of luck, and they probably also knew differential equations, and they actually walked away from a situation like that, which is a good news. And that's a fitting end to this chapter on applications of differential equations of order 1. They can be useful in life, but having luck is perhaps even more important. See you next time.